squared.
Write it as
1 squared, then
1 squared
plus 2 squared,
plus 2 squared
plus 3 squared.
And so on up to
Yes.
the term n. When r is taken up by n, it will be n squared is also equal to 1 over 6n into n plus 1 into 2n plus 1. Agree?
Yes, sir.
Good. And the other standard one that needs to be close to us is when you sum up from r equal to 1 to n of cube numbers. That is the quarter n into n plus 1, but each of them squared. If you don't write it like that, similarly, you would write it as alternatively the same statement, or you'd write it as, can someone reduce the series? Who can write down that series for us? I can assist it to note for you. Who can state it for us?
1 cubed plus
1 cubed plus
2 cubed.
Yes, plus
3 cubed. Plus
and so on
then
up to
n cubed.
That is what is equal to 1 over 4 n squared into n plus 1 all squared. Not so?
Yes. Yeah.
So now that kind of arrangement, that kind of those three we have recalled are paramount. They are very important when we are doing questions in the chapter. So having recalled them and knowing what each summation brings us to. So this is the sum of any terms of this kind of arrangement. This kind of statement can be abbreviated as the sum of any terms being equal to that statement. Similarly, this kind of order can be abbreviated as the sum of any terms being equal to that statement. In the same order, these terms here can be abbreviated as the sum of any terms of that kind being equal to that kind of statement. So why? Because you go up to the nth term. That's why you call it the sum of any terms. Very important. So in our examples, we want to appreciate those ideas. In our examples, we want to appreciate those ideas. Example 1, I will begin with that very one that we had tried out last time to just be on the same level. So number 1 was to find the sum of the following series. Find the sum of the following series. So the series at hand is 1 plus 2 plus 3 plus and so on up to the term 2n plus 1, up to that term, not the nth term, but up to that 2n plus 1 term. That's important. So the first terms, this kind of arrangement before the last term that we have been given looks like which one of the standard ones? 1 plus 2 plus 3 and so on looks like which one of these three? The first, second, or third?
The first one.
Good. So we will say, we'll just quote and say from the sum of any terms. Actually, better to first, since it's our first example, from this kind of summation, that it goes up to any terms, which is given by a half n into n plus 1. We know that this one here is the sum of any terms, and that sum is n into n plus 1. I can write it that way, over 2. But now I want the sum not up to any terms, but up to 2n plus 1 terms. So I will just do a substitution. They just want us to replace that n. Very simple. Replace that n there with the new n. So that last position has been replaced. Instead of n, they want us to feed there to n plus 1. So that implies that the sum of 2n plus 1 terms, 2n plus 1 terms of the same arrangement will mean where you have n, substitute 2n plus 1. Where you have n, substitute 2n plus 1, 2n plus 1 plus 1 over 2. Where you have n, you just feed into n plus 1. Is that step understood? Before we proceed, use the chat to talk to me.
Yes, sir.
Those who may be in a noisy place, just use the chat to alert me whether that point is understood. I'm happy that the numbers are increasing. That's wonderful. Faster. Sewanyana begs a pardon. Dosh also begs a pardon. Felix is okay. What about the others? What about the others? What do you say? Okay, all right. Responses are still coming in, but people just beg that I echo it one more time. It's a substitution statement. Let me re-echo it for clarity, such that for the consequent cases, we just see go on to do it directly. So what I've been saying that the standard sequence we have goes up to any terms, but the one we want goes up to 2n plus 1 terms. It doesn't. Actually, this one, if I'm to write it, I'm looking for the summation from r equal to 1, possibly up to 2n plus 1. Let me say so. But this one here, the standard one, this one here is the summation from r equal to 1 up to n. That's the difference. That n has been replaced by something else. Excuse. It's what I'm trying to say. So do you just have to do the same as well? Just come down here and say that now the sum I want, is the sum up to 2n plus 1 terms, which means that I should go to the sum of any terms and replace it with 2n plus 1. Go to the sum of any terms and n, replace it with 2n plus 1 over 2. So therefore, that means the sum of 2n plus 1 terms, which we are looking for, will be 2n plus 1 into 2n plus 2, if we agree. And that 2 can be cleared. That 2 in the second bracket is common. So therefore, the sum
Out of the K1
of 2n plus 1
so
factorize
the
out
K1
2 from here. This one, and that one give us a 2. That's why I have a 2 here. Is it okay?
okay.
So
Yeah.
that gives us 2n plus 1. I'm saying take out a 2, you'll get n plus 1 there. We are dividing by a 2. So these 2's can go out. Rather, they can cancel out to say. And that means, therefore, the 1 plus 2, this sum plus 3 plus, and so on, up to not n this time, but 2n plus 1 is the same as that sum is the same as n plus 1, I can begin with n plus 1 multiplied by 2n plus 1. That becomes the solution. That becomes the solution. The sum is n plus 1 into 2n plus 1. There we go. Example number 2. Example number 2 to further brainstorm. That will be part B. Want to find the sum of this series. Example number 2. There we go. Want to find the sum of that series. Want to find the sum of that series. Yeah, I'm doing an extra lesson of which you people are not planned for it. So bear with me a bit. So when you look at part B, class, it connects to which standard series? When you look at part B, which standard?
The second one.
The second.
The
Second.
Good. So having 1 squared, plus 2 squared plus 3 squared, we just recall the second series, which says that 1 squared plus 2 squared plus 3 squared, even if you go up to 4, but as long as you consider square terms, up to the nth term, n squared, gives us 1 out of 6 into n times n plus 1, or multiplied by 2n plus 1. So our interest is now not to stop at n, but to stop at a term to go up to a term n minus 1. It may be behind the nth. We want to end at n minus 1. End at the term n minus 1. So what is important is to know that this statement here, having observed that, is the sum of any terms. Represents the sum of any terms, which is the other statement, n into n plus 1 into 2n plus 1 all over 6. But what we want is not to go up to n this time, but to go up to n minus 1, to find the sum of n minus 1 terms. So what will this side become? Can I have one of us submit?
N minus 1 into
N,
bracket.
open brackets, n minus 1, good, into?
Open big bracket.
Open a big bracket, let me open it in red.
And then n minus 1 on a small bracket.
N minus 1 in a smaller bracket.
Plus 1.
Plus 1.
Then times bigger bracket. 2 into brackets.
2 into brackets.
N minus 1.
N minus 1.
Plus 1.
Plus 1. Thank you, Dosh. Thank you. So we simplify that. Let's simplify that together. So the sum up to n minus 1 terms will be n minus 1 into n. If you notice that negative 1 and that positive 1 will give you 0, into 2n minus 2 plus 1 out of 6. So the sum of n minus 1 terms will be n into n minus 1 into 2n minus 1, if people are able to notice that. We agree?
Yes.
So resultantly, I can list back the given statement: 1 squared plus 2 squared plus 3 squared plus up to the n minus 1 term, but of square numbers is 1 over 6n into n minus 1 into 2n minus 1. Is that okay? Is that okay, class?
What's the question?
Oh, the question is here. Find the sum of the following series. We are getting sums. We just don't want to expand. Those sums are suitable when factorized. So when you go further, you just see x, you may just expand, which is not necessary. That becomes the end. That expression, this value here is the answer. This is what they want to see. This one here is what the examiner wants to see. That what this series up to that point is equal to. Okay? Those who have just joined us, let's keep together. I'm happy that most of us are coming in. That's good. Part C. Part C. Part C. Part C. Here. Part C is here. Find the sum of that series. So if I may ask it duplicates up to the 2n terms, but the one up to n terms is which one that they are duplicating? 1, 2, or 3? In part C, what is being duplicated? Tosh says 3. Any other opinion? 1, 2, or 3? Okay, 2, 3, Nicholas says 3. We are looking at cubes, cubic terms. Each term is cubed. So that part C is a duplicate of the third type of series, the standard one. So we have to just refer to it. Simply say, what is 1 cubed summed up with 2 cubed, summed up with 3 cubed, and summed up with other terms up to the n term, up to any terms. That one is equal to a quarter n squared into n plus 1 whole squared. However, for us, we want to go not up to n, but up to 2n terms of that kind. So what we need to remember is that this one here is the sum of any terms of that type, which is equal to a quarter n squared into n plus 1 whole squared. What about if we want to get the sum up to the 2n terms, up to the 2nth position, not up to the nth just. So which is what will happen to this side over 4? Can I have someone submit? Thank you, Sawanyana, for discovering that. Any submission, what will happen?
N squared.
I beg your pardon?
N squared into bracket.
What will happen to the n? What will happen to that n?
Sir.
Yes, please.
Okay, for me, on my thinking, I think that you substitute n for 2n.
Yes, where there is n, we feed in 2n, correct? Then where there is n again here, feed there 2n plus 1. Are we there?
The squared is missing.
Yeah, the squared, square that one. Good, good, thank you. So what will our sum of 2n terms be? What will our sum of 2n terms be? Divided by 4. You will get a 4n squared times the 2n plus 1 all squared. I think you notice that the 4 cancels. We all see that the 4 cancels, and that sum, I will conclude it aside here. It will be n squared into 2n plus 1 all squared. Good. Thank you, Benjamin. Thank you, Dosh, for getting there. So therefore, our question 1, the sum of these terms, this kind of cube terms, up to the 2n terms but cubed is equal to n squared into 2n plus 1 all squared. That becomes a solution to that kind of problem. Thank you, Elvis, for getting there. It seems some people were already trying it out. I'm seeing the energy, and that's wonderful. Let's look at that as we graduate to another. We are going to employ the same things, but now at a bit higher level, or a bit more harder thinking problem. So we have seen how we can apply it in a simpler substitution way. Simpler substitution way. Okay, I believe people are brainstorming. Yes, those I just want people to stay alert. After understanding these 3, someone might think it's all done. Now let's think more. Let's think further as we proceed. This was the first example, Benjamin. We have not done a lot. Don't worry. Okay. Now let's add in ingredients. Let's add in ingredients. Part D. We are making it a little bit interesting. Okay, we are making it a little bit interesting. When you look at that statement, the nth term communicates. The nth term does communicate something. It communicates square numbers, terms that go up to n squared. Those are the square numbers whose general sum we know, but there is a 1 added on to it. There is a 1 added on to it. So that is a call to someone to be a bit alert. Let's focus and see how we can break this down. This kind of series which doesn't follow anywhere directly. It's not obvious that they have given us square terms, counting numbers, or cube numbers, the counting domain, no. But the nth term is communicating that there is a square, but added to a 1. There is a square number, but every square number obtained, they add on a 1. So that makes me look at this series, which is 2 plus 5 plus 10 plus and so on up to n squared plus 1. I'm forced to say what happened at the first position, because we know at the first position, at the first term, we set n to 1. When I set n to 1, in this nth term, because this is the nth term. The nth term is n squared plus 1. How do they get to? N is set to 1. So there is that term 1 squared plus 1. So I'm rewriting this series, but in not yet the evaluated way, plus 1. Then the 5 will be put down in the same way. That 5 will be put down in the same way, but as what inside there? That is when n is 2. You will have 2 squared plus 1. The nth term is guiding me. I've got it from here. Set n to 3. You will see yourself achieving that 10. But how does that 10 come about when n is 3? 3 squared. 3 squared plus 1. And that series continues like that up to the nth term n squared plus 1. Remember, we are looking for the sum. Is that breakdown understood? I want to pause there and get feedback. Is that breakdown understood? Is that breakdown understood?
It's fine, sir.
Yep. Thank you. Thank you. I see.
Yes, sir.
People responding in the chat. Thank you. So now, let's see. Let's now separate to our known sums. I'm now going to keep the 1 squared. I want to keep the 1 squared, then bring it to the 2 squared. After all, it's addition all through. Bring it closer, bring the 3 squared closer, and these kind of terms proceed up to n squared. That is how the square ones came about. They respected the n squared plus there is a 1 here. There is that 1. There is that 1. There is that 1. 3 1s corresponding to the other 3 square terms, and also they also proceed until the last 1. So there are many 1s, but we don't know how many they are. And what do you say in series? Ladies and gentlemen, I believe there's a lady in here. This is the sum of any terms. The standard arrangement, we know 1 squared plus 2 squared plus 3 squared up to n squared. This one whose sum we know. However, the ones that are being added up to the nth term, which is n squared plus 1, they are any ones. You simply get a repetition of the same constant up to the nth term. The number of such constants are that constant. It's a summation. Is that constant times the number of times you're doing it. We are doing it up to the nth term. So we are doing it any times. So what that 1 times n comes about, I can explain it. Like adding 2's. You add 2's 3 times. That is 6. But another person could say the 2's are being added 3 times because that is a countable number. 1, 2, 3. 2 times 3 gives me the 6. It's what I'm doing. Those ones were added any times up to the nth term. So this is the square numbers up to n squared. Those who are not here, we listed that. Square numbers up to n squared, it's here. The square numbers up to n squared, it's here. It's here. This one here is giving us 1/6 into n plus 1 into 2n plus 1. So when I come back down here, I will call this 1/6 n into n plus 1 into 2n plus 1, but adding on any ones, which is the same as n. So the required sum will be the required sum we are looking for. the required sum will equal to this sum here, n into n plus 1 into 2n plus 1, but over 6 plus this sum here of 1's, which is just n. Then I get the LCM to simplify. When I get the LCM, you all agree that the LCM is 6. 6 by 6 is 1. I get n into n plus 1 into 2n plus 1 plus 6n. And then that pushes me to say that n is common. I will not wait. N is common. Take out n. You remain with n plus 1 times that one, which gives you 2n squared plus plus n plus 2n, which is 3n plus 1 plus, when n goes out, that will remain as a 6. So our sum will be n into 2n squared plus 3n plus 7 all over a 6. So therefore this time around, the sum of 2 plus 5 plus 10 up to the nth term, which is n squared plus 1, is equal to 1 over 6n into 2n squared plus 3n plus 7. I don't know whether people have noticed that it was that quadratic wouldn't be factorizable. You wouldn't factorize it. That's why I've left it hanging. That's why I've left it hanging. That would be the solution to that. Are we good? Are we moving together?
So help scroll up.
Okay. Okay. I know that is the most important bit of all the steps.
Yes, sir.
Find that one. I want to modify 2 squared plus 4 squared plus 6 squared up to the 2n all squared, but with respect to the nth term. When n is 1, I should be able to get that first term too. When n is 1, I realize inside there it is 2 times 1, but all squared. When n is 2, it's 2 times 2, but all squared. That's how they come to 4 squared. When n is 3, it's 2 times 3, all squared. And so on, up to that nth term, 2n squared. My interest is to come up with that sum. Is that a breakdown understood? That breakdown understood? Members? Felix is okay. Benjamin is okay. Nicholas is not okay. Elvis is okay. Maybe one more shot. One more shot. I see Nicholas is not fine. Maybe one more shot to it. What I'm trying to say is, I'm using this nth term, the 2n all squared. But I have 3 terms that have been given to me, meaning I'm going to set n to 1, to 2, to 3. These are the positions that give me these terms. So when n is 1, feed in 1 here. You get 2 times 1 all squared. That's how that 2 comes about. Then when n is 2, that will be 2 times 2 all squared. And then when n is 3, you will get 2 times 3 all squared. That's how 2 times 1 is 2 all squared. 2 times 2, 4 all squared. 2 times 3, 6 all squared. Up to the nth term, which is 2 times n. Let me also write it that way. Now, I want you people to agree from indices that a times b raised to a power t is the same as a to the power t times b to power t. Distribute that power. This will be 2 squared times 1 squared plus 2 squared times 2 squared plus 2 squared times 3 squared plus and so on until the nth term, which is 2 squared times n squared. So what is that common factor? In all terms, even those we have not seen, those we have not been able to list, there is that common factor.
The 2
Is it just 2?
squared.
It is 2 squared. Now take it out. If you take out the 2 squared, that common factor you have identified, the first term will remain with the 1 squared. The second term will remain with the 2 squared, but one of them is out. The third term will remain with 3 squared. And the last term, the nth term, that last term will be with n squared. Am I right? Is that okay?
Yes, sir.
Good. Now I want us to agree that right now we are there simply because when you evaluate that outside term as 4, you will agree with me that this inside expression is the sum of any terms of such numbers that are squared. It's actually the same as this statement is the same as the summation of r equal to 1 to n of square numbers, the counting domain. So that one is the same as, what is its sum? Back to the reference above here, it's this quantity here that I'm referring to. I'm referring to this quantity here of square terms. So it's 1 over 6. It's 1 over 6. So it becomes 4 into, let me keep the bracket there, into that 1 over 6 multiplied by n into n plus 1 into 2n plus 1, close brackets. So when the 4 enters, when the 4 multiplies the 1 over 6, you will get 4 times 1 over 6 times n into n plus 1 into 2n plus 1. Reduce 4 by 6, what will you get? By 2, we'll get a 2. By 2 down here, I think you get a 3. N into n plus 1 into 2n plus 1. Yes, Benjamin. It's a proof,
Sir.
remember?
Sir,
Yes, please.
is there any proof that like the sum of square series is given by 1 out of 6, n into n plus 1 into
Yes,
n, 2n
the
plus
proof.
1?
The proof is the proof by induction, which we did. We confirmed that those series are true sums.
Okay,
That's
sir.
the proof, which we did. It's the proof by induction, which we did.
Okay, sir.
So 2 squared plus 4 squared plus 6 squared up to the 2n nth term squared is equal to 2 over 3n into n plus 1 into 2n plus 1. Remember, it was a proof, so we are good to say as required. As required. And unless otherwise, I want to do one more and then leave you to go and do other activities in the night, given what we are planning to do. Okay. That is our last number. Then I let you go to try that exercise. For anything, reach my inbox, and the next lesson tomorrow, you have to be kick-starting something new. So lastly, prove that the sum of the series of this is a third into that. Prove that the sum of the series to any terms is that. So it's possible that in that number, you have to notice that we have 1 times 2 added to a 2 times 3 added to a 3 times 4 added to a 4 times 5, and so on and so on. They are saying up to any terms. So the nth term this time around, it has not been given. It's the learner to identify the nth term for him or herself. The nth term has not been given. That's why the word is put in its real statement, any terms, without an expression. Am I clear? So in any term, to get the first term with set n to 1. N to 1, set n to 2, you will get 2, set n to 3. So it shows me that the first digit corresponds to n with respect to the position of that term. The first digit corresponds to n with respect to the position of that term until I'm generating the nth term. Hope people are attentive. Until the nth term, which will also begin with n. When n is 1, n. When n is 2, when n is 3. So the first digit corresponds to the position of the terms. But they are multiplying by a certain quantity. In each term, we are multiplying by a certain quantity. That quantity is what I want to find. In each term, we are multiplying by a certain quantity. With respect to the positions, what do you think that quantity should be? With respect to the positions, what is that quantity? So what do you do to 1 to get 2? That's how you can generate that expression. Yes, Benjamin. Yes, Benjamin. Benjamin, you deserve a mention. That's perfect. Cool. So it shows us that n plus 1, 1 plus 1 is 2. Then at the second position, 2 plus 1 gives us 3. At the third position, 3 plus 1 gives us the 4. At the fourth position, 4 plus 1 gives us 5. So the nth term becomes n into n plus 1. That's the nth term. So we have been able to achieve the nth term. We have been able to achieve the nth term. We have been able to achieve the nth term. So what do I do? So what are we supposed to say? To be safe, we can look at that nth term. The nth term, when it's simplified, you will get n squared plus n. You will get n squared plus n. You get n squared plus n. Now I'm using it to define up a series. When n is 1, what will it communicate? When n is 1, what will the nth term communicate? When n is 1, the nth term. Yes, please. So then I said feed in n here in the expanded format. When you feed in n as 1, the first term, that 2, will be 1 squared plus 1. I'm now generating a a series that is easy to handle. When n is 2, how did they get the 6? It's 2 squared plus 2. That is the 6. How do they achieve a 12? It is 3 squared. I'm using this format now. 3 squared plus 3. How do they achieve the 20? At the 4th position. 4 squared is 16 plus 4. That's how they achieve the 20 up to the nth term, n squared plus n. So I've generated known series, square terms and counting terms. So isolate the square terms first. 1 squared and 2 squared. The like one is 3 squared, 4 squared. Such terms go up to n squared. Then plus 1 plus 2 plus 3 plus such terms go up to n terms. I've separated it into 2. But this first one, we know it's sum. This first one, we know it's sum. It's 1 over 6, n into n plus 1 into 2n plus 1. Plus this side here, we know the sum of such up to n terms is a half, n into n plus 1. You need to refer to them easily. So the required sum is when you add them up. So required sum, the required sum is when I add these two, n into n plus 1 into 2n plus 1. I believe all of us agree that the LCM is 6 plus 6 by 2, that is a 3. 3n into n plus 1. So factorize out the common factor, which is n plus 1, n into n plus 1, leaving out 2n plus 1 here, plus a 3 there, all over a 6. So when you open in brackets, you get n plus 1, n into n plus 1 into 2n, that 1 plus that 3 give us a 4. So we notice a common factor 2, which when isolated out, you get n into n plus 1 into, put out a 2 there, this one here, you get n plus 2 over a 6. So that 2 reduces the 6, 2, and that 6 reduced to a fractional third. And then our required sum, so therefore the required sum becomes a third n into n plus 1 into n plus 2 as required. I believe that I've tried to summarize the chapter, does those few statements, and we are just left with keeping the practice on, keep the candle burning, and don't stop.